Hi folks, we're now moving on to talk then about a uniform electric field. A uniform electric field is an electric field that is constant. If you place a charge at any point in that field, then the force on that charge will be the same no matter where you place it. And we can produce a uniform electric field between two parallel metal plates with a constant voltage across them, a constant potential difference across them. So the electric force and the field strength are constant at all points in the field. Now you would do this by charging one of your metal plates, making it positively charged by removing electrons, and making the other metal plate negatively charged by adding electrons. And therefore the field between those two plates is constant. So if we place a charge in that field, it will experience the same force no matter where you put it. Interesting to notice as well, the arrows in that electric field diagram are all pointing down. They show you the direction that a positive charge would move, and the field lines are all parallel and the same distance apart to show you that the field is the same at all points between the plates. Now if electric field strength is the force per unit charge, if we rearrange that, then the electric force at any point will be the field strength times the size of the charge that you put in there. And there's what each of those quantities represents. Now, going back a wee bit then, the work that you do on a charge in a field, work done can either be the force times the distance, that was our National 5 work done equation, or from higher physics we said the work done on a charge by a field, W equals QV. Remember, we use a W for work done in higher physics to avoid confusion with E. That's because we use an E in this case for electric field strength. So W, the work done on a charge in an electric field, W equals QV, but that's also equal to the force acting on the charge times the distance that it moves. With another little bit of rearranging here for V on its own, V would be equal to the work done divided by the charge. But we can substitute in for F with EQ on the top line of that bottom relationship there. If F equals EQ, we end up with EQD over Q, the Q's cancel out, and we end up with E times T. So the potential difference, the voltage across a uniform electric field, is equal to the electric field strength times the distance between the plates. There it's there. Potential difference is the electric field strength times the distance between the plates. You could rearrange that relationship and say the electric field strength is the voltage divided by the distance between the plates, volts per meter. More about that in a little while. So potential difference, we've been talking about potential differences third year and told you not to worry about that term. We've said use the term voltage when we've been talking about batteries and electric circuits. But in higher physics we defined what potential difference was. It's the energy transferred per coulomb between 2 points in an electric field. W equals QV, so V equals W over Q, work done per unit charge. We can now also define potential difference though in terms of the electric field and the distance between 2 points in the field. If V equals ED, then potential difference is the work done in moving a unit positive charge in a uniform electric field across a distance d. Now remember, this is similar to how gravitational potential energy and gravitational potential are defined in a uniform gravitational field. Again, we did this down in National 5 when we told you EP equals mgh, and we were assuming that the Earth's gravitational field was a uniform field at the surface of the Earth, and we could use a constant for small g. So just like in gravitational potential energy, EP equals mgh. So our gravitational potential is gh, work done per unit mass. Our electrostatic equivalent, QED. Look at the similarity between mgh and QED. M was the mass, G is the field strength, H was the distance. Well, it's the same here. Q is the charge, E is the field strength, and D is the distance. And our electrostatic potential is the electric field strength times the distance, or the work done per unit charge. Sometimes it's easier to look at a little example with this. There's a negative charge in an electric field. Which way will it experience a force? Well, it will be repelled up from the bottom and attracted up to the top. It will experience a force upwards. Now, if this negative charge was an oil drop, and it had a mass of 2 times 10 to the minus 5 kilograms, and it had a negative charge of minus 6.4 times 10 to the minus 9 coulombs, and it was injected between 2 parallel plates that were 5 centimetres apart, and a voltage of 400 volts is applied across the plates, we could calculate the electric field strength here. Remember, V equals ED, and we could calculate the force that's acting on the oil drop at that location, and the direction of that force. Also, by considering the weight of the oil drop, determine the magnitude, that's the size, and the direction of the unbalanced force on the oil drop. And if there's an unbalanced force on it, we could calculate its acceleration. I think we'll do this on a separate note. Right, here we go. There's an awful lot of data in this question, so sometimes it helps to highlight the data. An oil drop of mass 2 times 10 to the minus 5 kilograms and charge minus 6.4 times 10 to the minus 9 coulombs is injected between 2 parallel plates 5 centimetres apart with a voltage of 400 volts across them. That's a lot of stuff there. I would make a list of that stuff. Just at the right hand side there. So there's our mass, 2 times 10 to the minus 5 kilograms. Very small oil drop. It's got a negative charge on it of minus 6.4 times 10 to the minus 9 coulombs. The distance between the plates is 5 centimetres. I would change that into metres right away. 0.05 metres. And the voltage across the plates, potential difference is 400 volts. And we have to calculate the electric field strength. So part A, we've got plenty of relationships to choose from now. So we could use electric field strength is the force per unit charge. Or we could also use V equals ED, that's for a uniform field. I think we'll probably be using that one. Because if the question's about a uniform field, I think we'll use the uniform field relationship for working out electric field strength. So let's get rid of that. We'll shuffle this one over. V equals ED. And we want to rearrange that to work out E. Remember, E is the electric field strength. Don't confuse it with energy. We'll use a W for energy if we need to. So E equals V over D. We know what V is. It's 400. And we know what D is. It's 0.05. So let's substitute them in. That's 400 divided by 0.05. Gives us an answer of 8,000. Now that's electric field strength. So you could put it in units of, well, volts per metre, because it's volts divided by distance, V over D, or newtons per coulomb. Either units there would be acceptable. Part B, part 1, calculate the electric force acting on the oil drop. Well, we can now use our other relationship that's got electric field strength in it, E equals F over Q, rearrange it for the electric force, F equals E times Q. We've just worked out what the electric field strength is, it's 8,000, and we know what size the charge is that we're placing in the field. It was 6.4 times 10 to the minus 9. Now I'm not putting the minus sign in because the minus sign just tells me it's a negative charge. I'll use the minus sign to indicate the direction it moves in. So that's the force. Do that in the calculator, you'll get an answer of 5.12 times 10 to the minus 5 newtons. That's the electric force acting on the oil drop. Now, which way is that going to act? Well, it's a negative charge. It's going to be repelled up from the bottom and attracted towards the top. So the direction of that force will be upwards. Okay, part C is by considering the weight of the oil drop. Well, let's consider the weight of the oil drop. The weight of the oil drop, W equals mg, and we know the mass of the oil drop from the question. It was 2 times 10 to the minus 5 kilograms. So right away we can work out what the weight of that oil drop is. And that weight will be acting downwards. So 2 times 10 to the minus 5 times 9.8 gives us 1.96 times 10 to the minus 4 newtons. Now the weight acts downwards. Let's draw this wee charge here and let's show that weight acting downwards of 1.96 times 10 to the minus 4 newtons. And we also know what the electric force is. The electric force acts upwards, and the electric force is 5.12 times 10 to the minus 5 newtons. Now that's upwards, so we can work out the unbalanced force, which is the difference between those two forces. The bigger force is down the way, so let's do 1.96 times 10 to the minus 4 minus 5.12 times 10 to the minus 5, and we get the unbalanced force of 1.45 times 10 to the minus 4 newtons, and that's going to be downwards. So the weight is bigger than the electric force. So if we've got an unbalanced force downwards, we can then work out what the acceleration of that charge will be, and that will also be in the downwards direction. So for part D, we're going to go back to our old friend Newton's second law, A equals F over m, where F is that unbalanced force, 1.45 times 10 to the minus 4, and the mass of the charge was given in the question, which is 2 times 10 to the minus 5 kilograms. It's a single oil drop, very small, and when you work that out on your calculator, we get an acceleration of 7.25 meters per second squared, downwards. You can get very high accelerations with electric charges, so watch out. Okay, that's a pretty tough question. How many marks was that worth? Let's see, 3, 6, 7, 11, 14 marks. 14 marks on a charge in an electric field. Pretty tricky. Now if you think about it, if we very carefully adjust the voltage across the plates, we should be able to get those two forces balanced, the weight of the oil drop downwards and the electric force acting on the oil drop upwards. And in fact, this was a very special experiment that was done in physics. This was the experiment that was done to determine the charge on a single electron. It's called Millikan's oil drop experiment. So let's look a wee bit more closely at that. Right, this is it. Millikan's oil drop experiment, as carried out by Robert Millikan, an American guy, 1900s, and what he did was he used charged oil drops to deduce the charge on a single electron. He sprayed negatively charged oil drops from a wee oil can into an electric field, and he adjusted the voltage across the electric field until the electric force upwards balanced the weight of the oil drop downwards. There's his apparatus. And when you spray the oil drops out of the wee oil can, as they come out the nozzle, they get a very slight negative charge on them. Same as when you spray an aerosol can, the particles come out negatively charged. He couldn't tell what the negative charge was on them though, but what he did was he let those oil drops fall into a uniform electric field at several thousand volts across it, and with a microscope he determined the diameter and hence the volume of one of the oil drops, focused in on one oil drop and adjusted the voltage until that oil drop was stationary or falling at a steady speed. Now if the oil drop was stationary or falling at a steady speed, he knew the forces acting on it were balanced. So if he knew the volume of the oil drop, from this and the density of the oil, he could determine the mass of the oil drop, he could then calculate the weight of the oil drop, and then he could calculate the electric force that was balancing that weight. And from the electric force, and from the electric field strength and the voltage and the distance between the plates, he could calculate the charge on a single oil drop. Not a single electron, a single oil drop. Now he repeated that thousands of times, and from those thousands of measurements what he found was that the charge on the oil drop was always a multiple of a basic unit of charge of 1.6 times 10 to the minus 19 coulombs. And that is still the value that we have for the charge on the electron today, 1.6 times 10 to the minus 19 coulombs. And that experiment goes down as one of the top 10 experiments ever carried out in physics, I think. And you could be asked about that in an exam using your electric field equations, uniform field equations, and your physics from further down the school, mass and weight and Newton's laws. So that's Millikan's oil drop experiment. Right, how did we look back to see if there was any past paper questions on charges in uniform electric fields? I had to go back quite far, 2007, question 5. It's Millikan's oil drop experiment. There's an oil drop with a mass of 1.2 times 10 to the minus 14 kilograms. It's stationary between two horizontal plates. There's a potential difference of 4.9 kilovolts between the plates, and the plates are 80 millimeters apart, as shown in figure 7. Now part 1 of the question says we have to draw a labelled diagram to show the forces acting on the oil drop. Well, in the first line of the question it says the oil drop is stationary, so those forces must be balanced. So let's draw a little oil drop here. There is a force acting down the way, and there is also a force on the oil drop up the way. And those forces must be balanced. The force downwards, of course, is the force due to gravity. That's the weight of the oil drop, mg. And the force upwards must be the electric force produced by that electric field. So there's our part 1 of the question. Remember it said draw a labelled diagram, so make sure your arrows are pointing the right way and it's labelled correctly. Part 2, calculate the charge on the oil drop. That's Q. Well, there's a couple of relationships we could use here where we could use the numbers in the question. So firstly then we've got the potential difference across the plates, V. V is equal to the electric field strength times the distance between the plates. And we've also got the electric field strength is the force per unit charge, E equals F over Q. And don't forget, in both those relationships, the capital E is the electric field strength. Now we can substitute the second relationship into the first one and get V equals FD over Q. We've substituted in F over Q for E, the electric field strength. And the F in that relationship, because these forces are balanced, the F is the weight downwards, which is equal to the electric force upwards. So mgd over Q. Mg is the force. Now, have we got everything we need? No, we need to rearrange for Q. So Q is mgd over V. Notice the similarity in that relationship between gravitational potential energy, mgh, and electrical potential energy, qv. Anyway, we've got a lot of numbers in the relationship here, so let's write them down. Mass, let's make a wee list. The mass of the oil drop was 1.2 times 10 to the minus 14 kilograms. G on Earth, 9.8 newtons per kilogram. D is the separation of the plates, the metal plates. It's 80 millimeters. I always change that into meters right away, so 0.08 meters. And the potential difference, the voltage across the plates, was 4.9 kilovolts. That's 4,900 volts. And we've got all the numbers that we need to pop into that relationship there. We've derived that relationship just from our basic, from 3 basic equations. So substituting in all the values for the mass, for G, for the distance between the plates, and for the voltage across the plates, 4,900, pop that into your calculator, gives you an answer of 1.92 times 10 to the minus 18 coulombs. That's not a single electron, that's the excess charge on the oil drop, the excess negative charge on the oil drop. And remember, Millikan found that that excess charge was always a multiple of the charge on the electron, 1.6 times 10 to the minus 19. So let's see how many excess electrons there are on that oil drop. Let's take that total charge, 1.92 times 10 to the minus 18, and divide it by the charge on a single electron. Let's see if it's a multiple of 1.6 times 10 to the minus 19. And if you do that on your calculator, you end up with 12. So the charge is quantized, 12 excess electrons on that oil drop. Lovely question. It's a long time ago. It's about time that cropped up again. Millikan's oil drop experiment. There you go then. See you in the next one.